Yeah, and greetings. Welcome to the Evidence Reasons Academy. There are a variety of people that ended up subscribing to this channel that was a little bit unintentional. Somehow YouTube directed a lot of people to my coverage of the Ukraine war, and a lot of my subscribers now might be interested in the Ukraine war. This is really an academic channel. We just covered both all sorts of variety of topics in science and current events. So I covered current events, and boy, my channel just about exploded. So um, just wanted to alert the subscribers. We're, we're privileged to have Paul Giem here. Um, I just need to mention, just for the sake of completeness, most of my uh, subscriber base probably shares my theological views, that is evangelical reformed, but I've invited people from all viewpoints, and from atheism to whatever, because this is what academic channels are for. And so that's just a little disclaimer, just so you know that you're going to hear all sorts of viewpoints aired here, and encourage people to study and learn, and decide for themselves what what they're going to believe or whatever. But today we're going to be talking mostly about science. Dr. Giem, please, if I may call you Paul, please feel free to introduce yourself to everybody and what we're covering tonight.
Well, I've been interested in the relationship between science and religion ever since I was a college student taking a double major in theology and chemistry. I continued that interest through the point that I went to medical school, at which point I also got a master's in religion. And beyond it, to where I actually wound up writing a book called Scientific Theology, trying to use not only trying to integrate science and religion, but also trying to use the method of science in theology, even though the subject matter is a little bit different. So the method has to be slightly modified. But there's a long history of the philosophy of science that actually probably is useful in theology. But whenever you're dealing with theology, you have to deal with the origin of life and the origin of the various kinds of life, and how that matches the standard scientific, what you would get in a course in a secular university. And by the way, thanks for the plug there. I would go on to say it's not just every Adventist scientist, but I think every conservative Christian scientist should know some of those things. I was speaking to my own community, but I think it has much broader ramifications than just Adventism itself.
I was very, just as an evangelical Christian, I just wanted to say I was very enthusiastic that you would join us in this discussion. So yes, that's my endorsement too. I just highlighted that comment by Jamie Russell because obviously you have a little fan club here, Paul.
Sounds like it, which is fine. I'd like to see it grow proportionate to the skill and care with which it's done, and the accuracy with which it reflects reality, which hopefully means it would grow fairly well, but we will see. we're going to be delving into a subject that most creationists have kind of shied away from. A specialized part of radiometric dating. And it was one point where I found myself uncomfortable shying away from, and at the same time being challenged to deal with the information by a somebody who was a AINO, Adventist in name only, and probably a CINO, a Christian in name only, who I can't make him feel bad because he is now deceased. So I guess he gets to figure out what to do in the judgment. But he was arguing for long age for life on Earth. He was arguing for an evolutionary history for biology. And when somebody came on campus who was advocating for intelligent design and not even creationism, he argued and argued and argued with the guy up front on the platform. So, and he threw this book at me called Absolute Age Determination, and it said, "Here, this will convince you that long ages are actually correct." And I read the book, and well, let's say I was less than convinced. And part of what we'll be talking about is why I am less than convinced. So I guess without too much further ado, unless you wanted more of an introduction, we could go straight into Spontaneity. And I'm getting loading here for some reason.
We're having some audio problems. Is your internet connection good? Hi guys, we lost Paul. Can you all see me? Can you hear me? He might have to log in. How about me? Can you see me? All right, I'll turn off my camera for a while. Okay, my camera's off. Let's see. Paul, try it.
I'm on now.
Okay. I shut off my camera. That might help a little bit. And go ahead.
You can take my camera off too, because I'm interested in people hearing what I have to say and looking at the slides more than looking at my face.
Sure.
But let's try it that way. Okay. So isochron dating. First, I should probably outline, because I'm not sure how many people are actually acquainted enough with radiometric dating in general and isochron dating in particular, that I can just start without giving some kind of a background. So let me try that. Radioactive materials decay exponentially with a formula that the parent material is equal to the original parent material times e to the minus lambda times t. Lambda is simply a radioactive decay constant. And it's related to the half-life by the half-life equals the natural logarithm of 2 divided by lambda. So by a few little maneuvers, and you can look them over if you want to, we finally get to t equals the natural logarithm of the original P parent concentration divided by the current parent concentration, all divided by lambda. The natural logarithm divided by lambda. And all we have to know to find a date, if the theory is correct, is lambda, the current parent concentration, and the original parent concentration. So that shouldn't be too bad, right? Well, now, almost all radiometric dating is that way. Carbon-14 dating is similar, but there's a difference, and I don't want to go down that rabbit hole, so I'm just going to point it out that it's there. We can measure lambda and P fairly easily. How much present parent element do we have? And what is the decay constant? And I'm going to try to avoid another rabbit hole, which is, has lambda always been constant? Now, P sub 0 can be calculated. It turns out to be a little bit complicated. It's the parent we have now plus the daughter that was produced by radioactivity. But the daughter that was produced by radioactivity is a little bit more complicated. It turns out to be the daughter we have now minus the daughter that we had originally, minus the daughter that might have gotten added somehow, and plus the daughter that might have gotten lost somehow. And we need to have all of those pretty well nailed down if we're going to be able to use the formula. That turns out to not be an easy task. For potassium argon dating, it is often assumed that the daughter at time 0 was 0, that the daughter added is 0, and that the daughter that has been lost is 0. So that it boils down to simply P plus D. Now, there's actually some more complications to that. And again, I'm going to point out a rabbit hole and try to step around it. The question is that assumption for potassium argon dating valid? And the short answer is maybe not. But let's get back to isochron datings. For some methods, dating methods, and I'm going to outline a few of them, the D0 is clearly not 0. And so that means we have to figure out what D0 was. I'm going to give you a few of those: rubidium strontium dating, samarium neodymium dating, lutetium hafnium dating, rhenium osmium dating, uranium lead dating. There are two kinds, although sometimes it's a model age. If you're talking about zircons, it's usually a model age rather than an isochron age. Thorium lead dating, potassium calcium dating, and rather surprisingly, potassium argon dating, which seems to indicate that maybe argon is sometimes retained. In fact, it's probably fair to say the evidence is in their favor, otherwise, in the favor of it being retained. Otherwise, we wouldn't even mention potassium argon dating in this setting. But there are actually isochron potassium argon dates, which just is weird. Now, the P0 can be calculated, as I said. What is done here is the assumption is made that the daughter product is homogenized with a reference isotope at time T0. So, for example, if it was strontium 87, it's homogenized with other strontium isotopes, and particularly strontium 86. And then a suite of minerals or rocks has more of the parent decay to the daughter in the standard way, but some of the minerals or rocks have a higher ratio of parent to reference isotope than others, so that eventually they have a higher ratio of daughter to reference isotope than others. And for the math phobic, close your eyes. This will all go away in a minute or so. In the case of rubidium strontium dating, P equals 87 rubidium, D equals 87 strontium, and R equals 86 strontium. And the derivation of the formula in the case of rubidium strontium dating is that. And I'm just going to have it up there for a half a second, and we'll move on, because I don't want you to actually study it. The fact of the matter is that there is no dispute over that formula itself. Excuse me. Should have brought some water. Note that the formula is of the form y equals b plus mx, or mx plus b if you prefer. And if you remember, that means we have a straight line. And that makes it nice, because we have all kinds of little formulas for calculating what a straight line is and which one goes by the most points and the most important points and so forth. And so we can get those little formulas out and calculate the slope of the line. And it turns out that the slope is e to the kt minus 1. And that means that we can take the natural logarithm of the slope, and we can find actually the slope minus 1, I think it is. And we can find e to the kt, and therefore we can find t. Okay, now here is an actual article, and you can see the reference underneath it, that gives you, it's 2020 article, so it's fairly recent, rubidium strontium dating, and you can see how all of the points kind of line up on that line. And you will notice that where you have calcite with practically no rubidium in it, or albite with practically no rubidium, that the strontium 86 to strontium 87 to strontium 86 ratio has not significantly changed. So you have this nice, lovely line. And this is just one example. There are others. Sometimes the data are a little more scattered. They don't like that, because theoretically it should be a straight line. The derivation of that formula gives you an exact straight line. But of course, in real life, things don't always line up exactly the way they're supposed to. Now, if you read G. Bernard Dalrymple, The Age of the Earth, which was published in 1991 and was written specifically to convince young age creationists that they should give up their ideas about the age of the Earth. He says on pages 108 and 109, for all practical purposes, the only way to move the isotopic composition of samples from one isochron to another is by either radioactive decay through time or complete isotopic rehomogenization. Points that fall on an isochron, by the way, the red is my emphasis, therefore, can confidently be interpreted as indicating the time of the last isotopic homogenization, that is, formation or reformation of the rock. Thus, the isochron method is self-checking, providing not only the prospect of an age, but also a statement on its validity. If you get a straight line, it means it's a real age, period. Now, it turns out Dalrymple is not quite correct. There is another process that can cause a straight line. It's called a two-component mixing line, and it always gives a straight line. And in fact, if you have three components and they start out in a straight line to begin with, you will still always get a straight line regardless of which ones you mix. And so you have two magmas that mix with each other, that diffuse a little bit into each other, and you take samples from magma 1 and magma 2, and maybe samples that are half magma 1 and half magma 2, or 3/4 magma 1 and 1/4 magma 2. When you line those things up, you will get that same exact straight line. And by the way, this is well known. And again, I'm going to leave these slides up for about 5-10 seconds so that you can take a picture of it if you need to and read this, although all of this stuff is in my paper. And it's a big, hairy derivation, but it's one that everybody, again, agrees with. There is no real controversy over the derivation of the mixing line. Now,
Paul,
yes.
can you go back to the prior slide? Because I'm a math guy. This is just beautiful. Can I just look at it and admire it for a little longer?
Sure. Drool, catch your saliva on the way out.
So that's just an expansion, okay. And then the result is?
And then it contracts again because a bunch of factors cancel out. And when you get done, you get that bottom line, which is D over R times a constant equals P over R times another constant plus a third constant, or AX plus BY equals C, which of course always gives you a straight line as long as, A and B are not the same numbers.
Okay, thank you.
Okay. Now, in order to give positive ages, a mixing line simply has to have a higher rubidium to strontium ratio in the component that has a higher 87 strontium to 86 ratio. And that is what you would expect if 87 rubidium had decayed to 87 strontium by either natural decay or accelerated decay. It doesn't matter. So now, the next question is, how do you tell the difference between mixing lines and isochron lines? Well, the lines themselves look exactly the same, so that doesn't help you. But there are three factors that could possibly make a decision. They are credibility, mixing hyperbole, and evidence as to whether strontium isotopes have indeed homogenized. So let's go through those. And you're going to say, well, that's not very precise, or, well, we'll see what we can find. In this particular case, we're after the truth. What about credibility? Well, some lines date in the future. I'm sorry, that's not an isochron line. It's got to be a mixing line. And everybody knows that. And if you want references, they're in the paper I wrote in 2003 that's on my website. Some lines date far enough in the past so that nobody believes it. What do you mean by that? Well, let me give you some examples. And again, the references are in my 2003 papers. I mean, these are all from the literature. I didn't even cull these from the literature. They were culled by that book that I was given, Absolute Age Determination, or I think in some cases by Faure. And there's, for example, lava that was dated geologically at less than 1.6 million years. How much less, we won't argue, but it's certainly less. And the rubidium strontium age was 773 million years. Nobody believes that. There's some 5.9 million, 5 to 9 million years by potassium argon age lava, whose rubidium strontium age is 31 to 39 million years. There's a less than 3,000-year-old lava that dates to 570 million years. Nobody believes that. Not if you're an evolutionist, you don't believe that. These were put out by people saying, see, you have to be careful. Less than 5.3 million year old lava, 870 million years. There's a less than 24 million year old volcanic rock. I don't know exactly what the difference between volcanic rock and lava is, but I suppose one would have to go back and look at the, I did once, but it has a rubidium strontium age of 1,200 million years, or 1.2 billion years, if you prefer. And then there's less than 5.3 million year old lava that gives you a rubidium strontium age of 1.5 billion years. That one, by the way, has made its way into the rate project. But they weren't the first people to have done the dates.
Dr. Paul?
Yes.
Just a just a quick question. Do you
Sure.
have access to the rate book? We're all dying. Some of us are dying for a copy. If there have been some that were public domain copies. If you don't have one, I just needed to throw that out.
I do have a copy of the rate book. I have a copy of I think both rate books, actually, the earliest one and the other one. That's partly because they quoted me and they had me review it a little bit.
Okay.
And so when you do that, they don't ask for the copy back. The other thing is that most of this stuff is actually available online.
I haven't been able to find it. I know it's available. It's just I haven't been able to find if they have a copy online.
Well, they have a copy of various chapters, and I think it includes all of them. But I'll tell you what, if you have a specific chapter that you want, I can look it up for you and see if I can help you out with that.
Okay, well, I didn't want to derail this. Please go on.
Sure.
Whenever my ears just lit up when you mentioned rate. Okay, please go on.
Yeah. Now, the interesting part of all of these dates here is that nobody said, well, can you prove that they're mixing lines? They just said, oh, it must be a mixing line. Because what else could it be? It couldn't be that something that, for example, lava that ran out of a volcano and less than 3,000 years ago, that's historical lava. And its rubidium strontium age was 570 million years. That just won't fly. So there's got to be some explanation. And the easy explanation is it's a mixing line. And why bother testing it further? Because it's a something. It looks like a good line. And there's not another good way of explaining that line other than either an isochron line, which again, nobody believes, or a mixing line. So I want you to notice what's happening. If you have data and it doesn't fit, you just say it's really a mixing line, and you don't bother having to prove that, or say, how can we tell so we don't make this mistake again? Now, what about dates that match long age expectations, but do not match short age expectations? Can we just simply are we stuck believing apparent isochron ages when we want to? Is it all subjective? Now, some would be happy with this, but frankly, I'm not. I think we should look for differing predictions using the different models and try to find out what is wrong with the other dates so that we can say, well, what about the disputed dates? Can we make any kind of decisions based on something other than it fits what I like? Well, there is something called mixing hyperbole. If you plot x versus y over z, as long as x and z both vary, and x does not equal a constant times z, or 1 over z, which would be a kind of a constant times z, or if one plots x over w versus y over z, and again, there's some conditions you have to put. W can't equal to k times z, or otherwise the math doesn't comes into straight lines instead of mixing line or some. I've forgotten all of the details on that. If you do that, you get a hyperbola, and the form is y over z equals c1, a constant 1, plus a constant 2, which gives you how big the hyperbola is, divided by x over w, or if w, if you're not dealing with a 4 thing, you just simply put x over 1, and it'll work. Minus a third constant. And C1 and C3 tells you how far you are from the y and x axis. I think C1 is the y axis and C2 is the x axis, but you could figure it out pretty easily. And there is a derivation, and I didn't put the derivation in because it's a long, hairy one. If you want it, it's in the paper, which is on my website. For example, we might plot strontium versus 81 strontium over 86 strontium, and we would get a mixing hyperbola. It's probably not going to be a straight line. It's going to be one of those curves. Unfortunately, when apparent isochron lines match long-age explanations, they are rarely tested to see if mixing hyperbolae are present. So, we were talking about those crazy ones. They didn't check for mixing hyperbola. So I don't know how good the mixing hyperbola would be to detect that this is not really an isochron line. Also, unfortunately, according to the book, isochron lines can produce mixing hyperbolae. Well, that makes it a little harder for us to be sure. I wonder, maybe isochron lines don't produce mixing hyperbolae. You can show that a mixing magma can produce mixing hyperbola, but it's not clear why isochron lines should produce mixing hyperbolae. But maybe all isochron lines aren't valid. That would be a stunning, maybe that's what's going on. Also, unfortunately, mixing lines do not have to produce mixing hyperbolae. I have that on the authority of Gunther Faure, Isotope Geology, 2nd edition, page 151. However, suites of samples formed by mixing two components may not fit a single mixing equation because the end members may have had variable isotopic and chemical compositions. Well, that sounds like they're not actually two-component mixing lines. Moreover, both chemical and isotopic compositions of rocks may be changed by processes occurring subsequent, that's his italics, to mixing, such as fractional crystallization, contamination by third components, and alteration by hydrothermal fluids or chemical weathering. Therefore, this is his conclusion, a certain amount, again, this is my emphasis, a certain amount of scatter of data points above and below the mixing equations is commonly observed for suites of geologic samples that are in fact binary mixtures. I do not know. It would be interesting to know, how far off you can get and what processes precisely there were. But it sounds like Faure is not willing to stake his life on if it doesn't have a mixing hyperbola, it isn't a mixing line. Just read that and digest it. It's wild. Okay. Now, we were with believability and we were looking at mixing lines. Well, we're getting into believability of isotopic homogenization. Now, remember, it is absolutely required if you're going to have an isochron that you have to mix if it's a rubidium strontium isochron, you have to mix the strontium 87 and strontium 86 isotopes completely throughout the mixture. If you don't do that, you will not get an isochron. You cannot get an isochron. And you would think that whole rock isochrons should match mineral isochrons because they're using the same process. However, according to Faure, igneous rocks of granitic composition may contain both mica minerals and potassium feldspar, all of which can be dated by the rubidium strontium method. Ideally, all minerals of an igneous rock should indicate the same date, which can then be regarded as the age of the rock. Oh, good. When mineral dates obtained from one rock specimen or from a suite of cogenetic igneous rocks are in agreement, they are said to be concordant. Unfortunately, again, this is my emphasis, discordance of mineral dates is more common than concordance. They usually don't match. That's just stunning. The reason is that the constituent minerals of a rock may gain or lose radiogenic strontium as a result of reheating during regional or contact metamorphism after crystallization from a magma. So these strontium isotopes are just migrating around on their own whenever. In such cases, the mineral dates generally are not reliable indicators of the age of the rock. We must therefore turn to the rocks themselves if we want to determine their ages. That is to say, the way you do this is you take a sample here, you take another sample from 10 meters away or perhaps a kilometer away, and another sample from further away than that. And then you run them through your process and you see if they line up. By the way, if you were curious, the mineral dates generally date younger than the whole rock dates. That means that when you can be confident that the strontium isotope, or more confident at least, that the strontium isotopes have homogenized, you're getting younger dates than the standard time scale, in some cases of an order of magnitude or more. Just wow. Now,
We can pause. I just wanted to say thank you for doing this. This is more data than I've ever gotten anywhere. And this is more hard. I liked especially the mathematical presentation you got, because a lot of the other creationists will not go into the details why it's unreliable. You've actually demonstrated the reason mechanically why it's unreliable, rather than just saying, oh, that doesn't work. We actually know that there's systemic problems in the dating. And
Yeah.
that is what's helpful, is when we can know why it's unreliable, rather than just saying it doesn't work. When you can demonstrate why it's likely to be unreliable just from physics, as you're demonstrating here, that is much more powerful argument. So I just want to express my sincere thanks. So please go on.
Okay. It seems to me intuitively easier to believe that the isotopes from this is a bad dictation, and I didn't catch it. Isotope migration between the minerals or homogenization between the minerals in a given rock, that happens more likely than between rocks which may be separated by meters to kilometers. However, usually rubidium strontium dates are done on rocks that are separated by those massive distances. Now, to be fair, on the other hand, rehomogenization of isotopes is easier to visualize within, various minerals of a hand specimen, say. So maybe the rocks do give the more reliable dates. Well, let's look at the physics just a little bit. I'm going to make 4 points. There may be others that other people could make, but these are the ones that occurred to me. Number 1, sedimentary rocks deposited underwater do not homogenize their strontium if the grain size, at least, of illite clay is 2 microns or larger. And maybe not even then. The limit is based on the assumption that long age dates are correct. Now, this is clay particles deposited underwater, and they do not homogenize their strontium dates, the strontium 87 to 86 ratio, unless the illite clay is less than 2 microns. Underwater. That's supposedly proven, and I have no reason to doubt it. Number 2, whole rock dating is sometimes assumed to be reasonably accurate when the whole rocks are separated by miles. The biggest one I can remember is 50 miles. In fact, in one case, because the rubidium strontium dates are younger than the other dates, it is assumed without further physical mixing, the strontium isotopes somehow equilibrated across the same distance after the rock was emplaced. Now, strontium is chemically related to calcium, which is mildly resistant to water solubility. In fact, strontium is worse. It's harder to dissolve. So they're asking you to believe that strontium migrates across miles. Just, jaw-dropping assumption if you think about it. And the strontium was able to do this without affecting the argon content of the rock, so that the potassium argon age was still correct. And I have a reference for it. I find that really difficult to swallow. And I really find it difficult to swallow when we realize that illite clay won't exchange strontium isotopes if the if the grain size is greater than 2 microns. So it's supposed to say put in illite clay, but it migrates across miles if you need it to. That just, to me, that just does not make sense. 3, there are several examples of lava which flowed in recent to Miocene times, whose rubidium strontium dates are in the 500 to 1500 million year range. We talked about that above. And the interesting thing is, those lava flows haven't equilibrated across miles. And I think everybody agrees that they haven't. And number 4, which is probably, to me, the most stunning of all, the experimental data are against easy migration of strontium atoms, at least according to Hansen and Gast, and I have a reference for that. On page 1120, they stated, and I am quoting, "It is significant that no one has so far been able to thermally induce radiogenic strontium-87 to leave its host mineral in quantities commensurate to the loss of argon under geologically reasonable conditions, even though it is not uncommon to find biotites in nature which have lost both radiogenic argon-40 and strontium-87 due to a thermal event." Oh, how do you know they've lost it? Because they date too low. What happened? Well, there must have been a thermal event. It must have migrated strontium ions. Wait a minute. You know, I haven't seen any data that would challenge that conclusion. Now, whole rock dating is sometimes assumed to be reasonably accurate when the whole rocks are separated by miles. In fact, in one case, because the rubidium strontium dates are younger than the other dates, it is assumed that without further physical mixing, the strontium isotopes somehow equilibrated across the same distance, miles. After the rock was emplaced, and this without affecting the argon content of the rock, so that the potassium argon age was still correct. So it's keeping the potassium, it's keeping the argon, it's somehow moving the strontium so that the rubidium strontium age has been reset. Miles. How do you do that physically? Well, what about matching dates? Well, I will say a couple of things. One of them is not all dates match, and the RATE project has shown some that don't. I don't know what the proportion of matching dates is, because on one side I'm seeing filtered data. On the creationist side, I have no idea whether they filter data, and if so, how much. So somebody needs to do that on unfiltered data. Now, even if we find matching dates, my paper went into some possible explanations of matching dates. And I think I can safely say that there isn't that much of a challenge for the mechanism involved.
Yeah,
but go ahead.
This is something I don't understand. So if I have a question, I'm sure maybe some of the people in the audience might. So a matching date does that mean that?
That means that the potassium argon date and the rubidium strontium date and the uranium lead date and the samarium neodymium date all give the same date.
Oh, okay. Thank you.
There are, or perhaps, for the same rock. And see, one of the things that was thrown at me when I presented this to some, shall we say, skeptics, was, well, but what do you do with the matching dates? Well, of course, the reverse question is, well, what do you do with all the non-matching dates?
Exactly.
And it's not fair to mention the matching dates unless you're prepared to mention the non-matching dates. Otherwise, that's known as cherry picking. And if you pick hard enough and long enough, you'll get cherries. It's guaranteed. My paper does go into possible naturalistic explanations. That's not a good way of putting it. Explanations that do not change the radiometric decay constants. And that's something we have to keep in mind. We may be, that may be the final answer. If it is, everything will fit perfectly. But there are other more complex models. And
sorry, Dr. Giem.
yes.
If it is, meaning if there is accelerated decay, that would fix everything, or
Pretty much.
Okay, can I just throw that out? I've actually been studying mechanisms. It's not accelerated decay, but there can be changes in nuclear structure. And I'm the first young Earth creationist to put it forward. It's from solid state physics. There's a lot of experimental evidence that under solid state conditions, the Coulomb force in the nuclei can be neutralized with heavy electron quasi-particles. So the collective behavior of the solid can actually make these quote unquote fictitious particles. They are not real particles, but you can model it like a real particle, as if you had a heavy, slow-moving electron that goes to the nuclei. And it's really the collective charge distribution in there that it can sometimes lower the Coulomb barrier, and you can get changes to nuclear structure. So there's all sorts of interesting experiments to that effect that are people had dismissed it for very long, but we're starting to see experimental evidence in the chemical labs. So I have really focused on that this last year. That's why I started to get very excited, because independent of one's view of the age of the Earth, this is just really cool nuclear physics.
Part of why I'm saying things the way I am is because if I had to bet, I would bet against accelerated decay being a major answer. But that's not the same thing as knowing for sure that it's wrong. And I don't want to foreclose stuff.
And it's not accelerated decay. It's the ability to change nuclear structure, and it will give very definite proportions of the chemicals.
No, what I'm saying is that there, as you know, there are other hypotheses out there. And some of them actually have some data to back them up, although I'm not sure that they answer the entire question. One of the things that I said was that, and I said it to these people, that the Humphreys et al. Uranium helium experiments were fascinating, but they really need to be sure that it worked in more than one place before they made too much of it. Science is a study of the reproducible, and if you can't reproduce the data somewhere else with a similar temperature gradient, I don't think you have all that much. You have something interesting, but in medicine, one study is no studies. And I think we have to hold ourselves to the same standard that we would if somebody were arguing on the other side. So I'm I'm cautious not to tell people they're wrong until I'm sure, because we've made that mistake before in a number of different ways, and certainly we've made it in medicine. People were absolutely sure that, for example, bacteria had nothing to do with ulcers. And the evidence is overwhelming that they were wrong. And I was one of those people. So, let's have a little more humility. So I'm going to say that if the mathematics works out, that if there was such a thing as accelerated decay, it would answer all of the questions, or most of them. But I'm going to say that there are some other explanations that also mathematically will work, and I've given a few of them here. And there are some explanations that some other people have come up with since I wrote the paper. And that was what I was referring to with the Southern California batholiths there.
Well, I don't want to derail your discussion, but what I'm going to do is I'm going to send you the article that I got very fascinated with. I'll tell you, there's another reason I was fascinated with it. There's an anomalous concentration of uranium on the continents versus the seafloor. There's 70 times more uranium on the continents than on the seafloor, and I'm just like, well, that's
fascinating.
and what mechanism can cause that? So let me just throw out some things. I'm sorry to pause, but I feel also my professional responsibility to alert you to some developments.
Sure.
The prestigious scientific journal Nature called out an experiment that the faculty in Italy said these guys are cranks, but so it was a faculty battle. The people on one side of the argument said we were able to detect neutrons when we were just compressing granite. And I was like, I'd say they're cranks and they're liars or whatever. But there were also other respected chemists having similar experiments getting mild amounts of transmutation. I'm not talking large.
Yeah.
And so Nature covered that, and I'm just like, I saw the paper, and I said, until we had a mechanism, I'd be dismissive, but I had enough solid state physics to know about all these things called quasi-particles. And so, for example, the transistors work because of quasi-particles. They're called they're called holes. But now in modern computing, we're using all these other ones like polaritons, and they're just all these other quasi-particles. And one of them's the heavy electron quasi-particle that's about the weight. It is comparable to the muon. It's not as heavy, but we're able to catalyze nuclear transmutations with muons at low temperature. We can do it also then with heavy electrons. And then now I began to be excited because even mild amounts of electricity that can be generated piezoelectrically or tribo, because we know that during tectonic events, there's a lot of electrical activity, and now it's becoming universally accepted that there's a lot of electrical activity down there in the earth. With pressure and electricity, you may be able to get a variety of isotopes, and also there seems to be kind of like a native state. And this has also arisen in the question of nucleosynthesis in general, because we don't know how a lot of, either God created all the elements in their isotopic proportions, or there was some other, he created it through starting with water or something. But in any case, just needed to alert you. I sent you the paper now that had catalysis by heavy electron quasi-particles. It only came out last year. And this is definitely in the field, my personal field of interest.
Looks like we just got it.
Yeah, I think you're going to enjoy it, even if you don't agree with the final conclusions. They cite a lot of experimental evidence, and I think you're just going to have fun just reading it, independent of young Earth creationism or radiometric dating.
It's cool that you can transmute elements.
Yeah. So I just leave it at that, and I've derailed you long enough, but thank you.
Well, anyway, so some other people were working on the Southern California batholith. They were creationists, by the way, and they proposed that the batholiths were made by mixing two magmas with precipitates that came out of them. Two different precipitates, one from magma 1 and one from magma 2, and then the two magmas mix, and then you get, well, that would give you some nice fake isochron lines. And in fact, it would give you possibly reduced age fake isochron lines. So there's a bunch of possibilities in terms of what could explain not only dates, but matching dates at times. And nobody's really even started to work on this stuff because I think most people have not been aware of it. Evolutionists have largely, not have just simply taken the dates mostly at face value, and creationists haven't really gotten into this. So nobody's asking foundational questions that need to be asked. But anyway, when I presented my paper, I was presenting it at a quasi-debate. There were dueling papers. The other paper spent 47% of its time arguing that if decay constants changed, the universe would fall apart. I didn't know God was that constrained, but and he was kind of bitter that he was felt to be a non-Christian because of his views on the age of the earth. Well, and but he could be, people could be skeptical of how seriously he took the Bible. I think that would be fair. And the crazy part of it is that he had my paper before he sent in his presentation, because we sent in our papers, and then at the conference we read them, and then as much interaction as could be had, we interacted with each other. But in this particular case, he didn't interact with me at all. He mentioned it only in passing, and I'll just give you that. This is a little piece of his paper. And reading his paper, this is, of course, is only the most commonly heard objection to age dating of rocks, that is to say, change in the decay constant. You may have heard other objections, such as scientists only publish some of their data. Well, that's true. Inconsistent ages reported between methods. That's also true, but mixing lines explaining linear isochrons. That is, of course, what my paper was about. So he mentioned it once. And then he goes on to say, but geochronologists find all these other arguments unconvincing, even the more technically sophisticated ones. Which I don't know. Maybe he meant mine at that point. These explanations either fail outright or are examples of biased induction that can't explain the data as well as the simple explanation that the rocks really are the age that the radioactive clocks say they are. So that's what he said. I just, it's like we're talking past each other. And it wasn't for my lack of trying, because I sent him the entire presentation and the paper and everything so that he could critique it. Because it is my firm belief that if you walk in and you surprise somebody and they don't have an answer, you haven't proved a thing. Since then, there has been a discussion on Peaceful Science. That's the Joshua Swamidass website, where I wound up discussing it, and the link is right there. And my biggest plea in the discussion, we went all around a lot of this stuff, was that we needed to do isochron and indeed radiometric dates blinded to the geologic horizon and then report all the data. This is what you would do if you were doing a medical test, especially when you have dates that you could throw out or keep depending on how you felt. No, you want to have the commission or commitment to, this is a good date, before you see the answer. Because
I've been on this peaceful science. It's a cesspool now. Some of them, I've had a very bad experience there. Even when I probably something you'll appreciate, when I gave very clear stuff on the origin of life, they're just awful. I'm just like, guys, you could admit I'm right. This is some basic chemistry. They would not give an inch. I'm like, okay.
They wouldn't give an inch on the origin of life. Is that what I heard?
Yeah, I was talking about the stairway of life, and they wouldn't give an inch, and they're just doing lots of ad hominems. And I got pretty tired of it. And I mean, I participated because at the time they didn't know it. I was getting a lot of data for, I was getting a lot of data and getting editorial revisions for a couple scientific papers that eventually got published, including one that went into a Springer Nature publication that's now on university library shelves. So that I did put up with it for a specific reason, and they actually helped me on some other papers just to clean them up. I'm not there just to debate and argue and
Yeah.
they actually cleaned up some of my papers really good, and they gave me all this free editorial peer review, and so the stuff we were writing is just starting to sail through peer review. But I got tired of dealing with them. I just needed to mention I expected that they would treat you bad. But anyway, please go on.
Well, see, I can live with their not being convinced. For one thing, for some of them, it would mean upsetting their entire theology, politics, everything. And people don't give that up on a whim. But I am really surprised that nobody, I mean, it sounds like the people you were dealing with were worse than Dawkins, because Dawkins at least has said out loud that nobody has any idea of how the origin of life happened. And that in and of itself should give somebody a little tiny bit of humility. But apparently either they're totally dense or they're self-deceptive to an amazing degree. Because I mean, I can understand somebody not wanting to say, well, you got it right, but I would at least expect people to say, well, I'm not quite sure how that works.
Well, I got to tell you a funny anecdote. They were so hostile to everything I said. I started just quoting, just as a prank, quasi prank. I started stating stuff straight from a textbook, mainstream textbook. Some of the data
without putting quotes in.
I'm sorry.
Without putting quotes in.
No, exactly. I just said, okay, we have readers, writers, and erasers that modify histones. This is in like the back chapters of Leniger edition 5.
Yeah.
Leniger Biochemistry edition 2.
Yep.
They flipped out and said, "You're stupid." I just laughed. I said, "Okay, you think I'm stupid? I started quoting the peer-reviewed literature. I said, "You're wrong, guys." And one of them was an evolutionary biologist. I humiliated him.
What did he do then?
Oh, he just, what they usually do, they just change the subject and never back down and just
Oh,
keep
that's
insisting.
fine. That's fine. I'll take that.
Yeah. And, and so it's like, okay, see, I can admit I was wrong, and then that's editorial corrections for my peer-reviewed papers. But publicly, they have to act as if they're so much more superior. And some of these guys I've debated for 20 years before when I didn't have any graduate degrees, had no biology, didn't have a physics graduate degree. And the longer I stayed in school and started having better arguments with them, the more they resented. So there's a proverb: correct a fool and he'll hate you. Correct a wise man, he'll love you. Correct a fool, he'll hate you.
Yeah.
And I just wanted to just say the reaction at Peaceful Science was not at all surprising. And I think they really resented it when I started getting into peer review. I'm just like, okay,
Well, I think that
secular peer review.
the paper held its own reasonably well.
Yeah.
That they were not able to find any specific things that they could criticize and say, oh, you goofed it here, oh, you goofed it there. So, I think this stuff is pretty solid. Now, to summarize, isochron lines can theoretically indicate time. They can. But mixing lines can mimic isochron lines, but have no necessary relationship to time. And it can be very hard to tell the difference between mixing lines versus isochron lines. Some apparent isochron lines are certainly mixing lines, and everybody concedes that. Experimentally, strontium does not migrate as easily as is required by long age theory and by isochron theory. And finally, there are models that can account for multiple reduced age isochrons lines that are roughly or even exactly matching to each other in terms of the date without invoking time.
And okay, even if, by the way, I just needed to mention we have people who are old Earth creationists that watch this, and I consider them dear brothers because they are creationists. They just have a different model for the chronology. But
That's fine.
What you've laid out here should be interest to everyone, because let's just assume that even the Earth hypothetically is old. You still would want to be able to have reliable dating methods for the events. And this is telling me this is not a good state.
Yeah.
Even if hypothetically it were millions and hundreds of millions of years old, with these dating methods, you can't really establish the time of these events. You just say it's old, but you can't affix reliable dates to this with these methods. And so your earlier equations that you began the slideshow with were really impressive.
Well, I will have to say they're not my equations. I did recreate them, starting with, if you begin at the beginning and you follow the math, you'll get to the end. But a bunch of people have done that before me, and their equations match mine. This is not, this is not due to my brilliance. This is due to, well, I guess maybe some brilliance in being able to recreate it, but not brilliance in terms of originating it. This is just standard stuff. If you open Fare, you'll find some of those same derivations. It's just not that big a deal. Now, to go on, I think short age models may in fact be superior to long age models in this area. And I think this is an area that needs continued work. But kind of the bottom line is that short-age creationists need not uncritically accept the standard long-age interpretation of radiometric dates. That would be my conclusion. And I'm open to questions and comments.
Yes, in the audience, just tag me if you have a question or comment. I will say this, the one that really does, still to this day still gets my attention, even if I weren't a young Earth creationist, is the concentration of uranium is 70 times higher on the continents than the seafloor, and presumably the mantle. And it's like this doesn't square with us getting uranium from a supernova. So they've had to come up with all sorts of alternative theories where uranium kind of got sprinkled on the surface of the Earth. And then it's like, okay, if you invoke that, how come it's on the continental shelves and not on the mantle? You would need some very fortuitous timing. And that's why, sincerely, I tell my old Earth creationist friends, I can't just run away from that. And if we are able to synthesize, we've had experiments that may have been able to synthesize uranium from copper or other, elements lower on the periodic table, lower atomic numbers. I'm sorry.
Is that with a massive electrical discharge?
That's one. That's one of them. But that's the one that was the experiments in Kiev in Ukraine, and I saw the paper in Russian. And where they got the idea was they're trying to solve the problem of stellar nucleosynthesis, and they're talking about these electron gases or something, or these relativistic neutron gas. I forgot what it was, but it was the basis of that where they call it quantum attraction. And yes, we might be able to have it at high energies, but I said I really want to see if we can synthesize these at low energies. So the paper I sent you on heavy electron catalysis of transmutation, my jaw dropped when I saw all the transmutation experiments, and they're able to generate a variety of elements, and then also the isotopic proportions were very interesting. So I look forward to us just having fun with that. I went through the paper. I did a reading of it once. So I think it really is, in some sense, there are a lot of exciting frontiers of what we thought we knew. Even stuff that we had totally dismissed and said we can't have low temperature transmutations of this variety. And if we do, this is going to be a lot of fun. So Schnoil says, thanks a lot for your presentation, Dr. Giem. That was amazing. Can you go back to your first slide? Unless I see any, I'd like to acknowledge also Robert Beatty here. He was trying to contact me. I had to just pause a little bit to address him because he has some important stuff.
You're talking about this one here?
Yeah, yes, if you can move it forward a little bit. I loved your where you had the P's and the D's. Okay, that's good. And then you move maybe the next slide. That one. So P, okay, D stands for
Daughter.
daughter. Okay. And
If
so D,
my atom makes a daughter atom,
okay,
then the original has to be the parent atoms that we can find now, plus the daughter atoms that have been made. But the daughter atoms that have been made has to be calculated by the daughter atoms we have now, plus any that have been, adding back in the ones that have been lost and subtracting the ones that have been added, and subtracting the daughter elements that we had at the very beginning. And you see, for potassium argon, the theory is that all that argon disappears when you heat the rock up to melt it. But in strontium, you don't get rid of the daughter element, so it's still there. So now you have to find the daughter that was there originally, and that becomes an interesting problem.
Okay, that answered my question. I'm going to get to Mr. Jetty's, but look at this. This was this controversial experiment by Carpentieri, piezonuclear fission, which I don't think it is. I really do think it's heavy electron catalysis. But they were getting neutrons out of this, and this is where nature said there was a huge scandal where they're compressing granite and getting neutrons. So how does that relate to this whole thing about uranium on the continents? I think if there's tectonic activity and it created the uranium, I think that would account for it. It would also be proof of a huge cataclysm where there was a lot of compression and electricity. And so he's saying has 30,000 citations. People are excited about this. People said they're cranks. And I would lean toward them until I read the paper on heavy electron catalysis. Now, Mr. Jetty has a question. And you actually talked about it a little earlier about zircons. And you said that the creationist view needs, like say the helium in zircons, you felt that we don't have a large enough sample size as creationists, but I will just let you answer this one. Mr. Jetty works on a particle accelerator, and he's an older creationist, so he and I have different views of things, but I respect him. He's a brother in Christ, and I totally respect any time that he'll disagree with me because he's knowledgeable. So just wanted to introduce you to who he is.
Okay. Well, I cannot say how I would age zircons. That sounds a little weird. It is a little weird. But I am in possession of some raw data that suggests that model age of zircons, which is different from isochron age, is unreliable. I suspect that the answer for why it's unreliable is that zircons can inherit ages right through right through everything being melted. Now, the reason that I cannot say is because there are a couple of papers that have not been published that I'm keeping my mouth shut about until they're published. They're by friends of mine.
Yes, you don't have to mention their names. I know who they are.
I'm not going to mention their names, and you probably do know who they are, but we will leave that unannounced because obviously we don't want to prejudice any jury against them.
Exactly.
I have suggested to the same group that one of the experiments we should do eventually, and it may not turn out well, but if it does turn out well, could be a game changer, is to date zircons from modern day lava. Particularly lava that has been in a lava lake for a while. If we can find zircons, and that's a big if, because some of those things are zirconium poor and therefore don't make a lot of zircons, and may not have inherited a lot of zircons. We may not be able to find it. And if we do dates on them and they carry inherited ages, I think the game is up. Now, will that happen? I don't know. But it's fascinating to try to find out. I mean, after all, if I can put it this way, the whole purpose of science is to go out and find out whether your hypothesis is correct. And it's an interesting hypothesis. and it's worth spending some time trying to find out if it's correct. Now, I can guarantee you that if we find, well, if it's said in a particular way, it might get published as well in the secular literature. But you would have to be very careful about how you said it. And you could not draw all of the conclusions that would be reasonable from it. You would have to simply go in there. We did this. We found this. It is not clear how this fits into standard models, and let it go at that.
That's about the only way you can get away with stuff like that. So we propose some other experiments just to recap from some of our other conversations before we wrap this up. There was experiments you propose with testing for uranium concentrations in when we find coals that have certain C14 signatures, and then also beryllium 10. So maybe we could just close with that. I'm starting to redevelop my aches and pains from last week. That's why I'm starting to slouch a little bit. I think some of this is because of just ergonomics of how my setup needs to be modified.
Well, I probably had you leaning into the screen too much with the presentation, so my apologies.
Well, that can be corrected when I fix my ergonomic setup. So but all this to say, I'm probably running out of gas here. So
Sure.
we wanted to cover. So you mentioned the experiment with zircons, and that was a very good question. Thank you, Mr. Jetty, about the age of zircon. And so you had the C14 experiment, and then also the beryllium 10, which is cosmogenic dating for beryllium 10.
Right. Well, C14 is also cosmogenic most of the time.
Oh, that's right. Thank you. Okay.
It's if you go through Guy and Schleicher, they have it in the cosmogenic section, just in case I hadn't caught it already.
Well, see, this is great. You've reviewed so much of the secular literature, and you've been very thorough. It's just not been. This is one area that I haven't spent a lot of time in because I've been studying biology for for a long time.
Well, I'll tell you what, you and some of our other people who are listening might find it interesting to read Chapter 5 of Scientific Theology, because that goes into it pretty heavily, and it's still mostly good. It has aged pretty well.
So, Danish debater, we have a lot of people who are from across the pond, that is across the Atlantic. And so they drop in at various times, and Danish debater is one of them. And he's just asking what we're talking about. So we're talking about radiometric dating. Just wanted to update him. Okay, so
specifically isochron dating.
Isochron dating. Isochron dating does require radiometric dating. Is that correct?
It is a form of radiometric dating, correct?
Okay, so the hypothesis is that we can. One experiment is we want to see if we put a lump of uranium or a neutron source, whether we actually do get C14 beside a piece of coal or something like that. What the prediction of the radiometric date would be. So that was interesting. And then beryllium 10, can you cover what the experiment was? We should dig somewhere like.
We should start out by measuring in the Columbia basalt. We should measure the beryllium 10 concentration in areas that should be shielded from cosmic rays. Basically, go down a borehole for a well or something like that, and just take some of the samples from, say, 10 meters down and 20 meters down and 30 meters down, and see whether the beryllium 10 concentration decreases with depth, and by how much. If it does, then the explanation of it being created on the surface by muons would be supported, corroborated. You never want to say proved. If it doesn't, then that raises some huge questions as to how the source of the Columbia basalt kept its beryllium 10 concentration for 18 million years.
Well, I'll tell you why that's of interest to me, because the racemization, the chemical dates seem to have some
14
very,
million. Go ahead.
I'm sorry.
14 million years, not 18.
Okay.
Go
The
ahead.
reason that's of interest to me, the chemical dates have um, a distressing lack of variance, meaning we've been finding unracemized amino acids all the way down to the Cambrian. I found a paper on that from like the 1960s. And the reason they don't find that anymore is if you find it, they're going to assume it's contamination, and no one will accept it in the mainstream peer review. But we can actually remake these observations if people are willing to. And I began to say,
And make them anyway. And if we get stonewalled, publish it in creationist literature. Just be viciously critical of it, so that when people say, "But you didn't think about this, and you didn't think about this," you can say, "Well, actually, we did."
and the thing is it's still an interesting data point, and the reason that it's starting to go that direction is because of Mary Schweitzer's discovery of soft dinosaur tissue.
Mm-hmm.
The chemical states of the soft tissue, independent of the fact that it just looks soft. The chemical dates, I talked to Brian Thomas at the ICR. He said, "What are you doing? How do we end up with peptide bonds there lasting this long?" That's one. And then Jay Weil was pointing out there's some other things with oxidation, and then there are other things, if we check for racemization, there are just all sorts of things that don't add up. And so they're now coming up with they're saying, well, we might have to revise chemical kinetics. I'm just laughing. Yeah, it's like, try, you know. Um, so this whole thing where you said there's an invariance, we should look for an invariance of beryllium 10 all the way down to the layers. So say even if we find it in the Cambrian, I don't know if you get basalts that deep.
Oh no, you would actually do it within the basalt layer.
Okay.
But
So
here's the thing. Then what you can do is you can go to another basalt, like the Deccan traps in India, which are 55 million years old, and the Siberian traps in Russia, which are 200 million years old, 240, I think. Whatever, and see if they still have beryllium 10, and see whether it's homogeneous all the way through them. At some point you have to start saying something is wrong here.
Well, we're going to have to find some scientists that are not from NATO countries or the Ukraine to go out there and dig in Siberia.
Well, who knows? Maybe in another year we'll be able to do it.
Yeah, I hope so. Well, Dr. Giem, if you have any closing words, and I want to sincerely thank you for this tremendous presentation. Please, if you have any closing words, and I'll try to put some links in the video description to scientific theology after we're done. And anything else you'd like me to link to, I can do that. Just let me know through email or something.
Well, I think I would close with the same plea I made the last time, which is always keep in mind that if we win everything, but we're total jerks while we do it, and we influence people to say, if that's what Christianity is like, I don't want anything to do with it, we have not won. That that we are told that by this shall all men know that ye are my disciples, not that you have answers for isochron dating, but that you love one another. And by the way, that includes, Sal and I come from different perspectives, and that means that we have different opinions on some theological issues. I have differences of opinion from some people in my own church, and Sal probably has people in his church who have theological differences with him. But theological correctness is not the final answer. If it were, the disciples at Jesus' resurrection would have been in deep weeds. In fact, at his ascension, they've had all this time to speak, to think about what's going on. And then he's just getting ready to go up into heaven. And the disciples then say, Lord, is this the time when you are going to restore the kingdom to Israel? And I'm sure that Jesus inwardly is just going, I don't believe this. Well, he was going, yeah, I do believe this because I know what's going on. But he graciously said, it is not for you to know the times. So people who have been with Jesus for 3.5 years still didn't get it. We shouldn't be surprised if we don't get it all the time. All of us, and that includes me. And that means that we really don't get it in terms of science, because we have less clear indications in science than we do in scripture. So a huge dose of humility is in order, and I need to swallow my medicine along with everybody else.
All right. Well, I'm just Paul. I'm sure we'll meet again. I'm just going to shut the stream down. I'm going to play some music to just give us a little bit more gracious ending. So thank you again very much, and God bless you, sir. And thank you all. I could speak on behalf of all the viewers, and Janet Duttridge is here. Hang on, Janet. I have a gift for you, Janet. Before you leave, I'm going to make you a moderator. So you're now a moderator, and so congrats on being a moderator, Janet. All right, Paul, take care. Everyone take care, and God bless you. Have a good evening.
Thank you.